Alrighty, let's get started. Okay, before we kick off for today, for those who didn't see, there will be makeup office hours today at 4 o'clock. And so feel free to come and chat then. Just as a reminder, the project proposals are going to be due tomorrow by the end of the day. So do make sure to get that done. And let me bring up the chat so I don't miss anyone. So yeah, if anyone has any questions about that, if it's short, we can discuss that now or come to office hours.
Alan, is there like any kind of prompt for the proposal posted, or is it like embedded in the notes? We wanted to kind of refer back to it.
Yeah, so I think I gave a little bit of information in a set of slides. I can post that on Canvas so you guys can reference that. But it's pretty kind of free form. Yeah, basically looking for what your main ideas for the analysis are, and then at least a preliminary look at the data. And so none of this is like binding. So if it changes in the future, that's fine. But it'll be helpful for folks to at least start looking at the data.
I have a quick question about the project. Is that you said that we can do some sort of a regression or unsupervised learning for the project, but since we haven't really covered the unsupervised learning aspect yet, like what are the types of, could you like give an overview like very briefly of just like what are those types of things that we could consider for this project?
In reference to unsupervised learning?
Yeah, because I just feel like we don't really have an idea yet of what that is or how.
Yeah. Yeah, we cover that a little bit later, but so I'll talk a little bit about what you can think about for that, but I would say even before you think of a technique or tool, and I think this is kind of in general, when you consider a data set, I don't think the best approach is necessarily to say, oh, I want to apply, this technique to this data set. It should be more driven by the question that you're interested in. That having been said, like if you don't know your full tool set, that can be tricky as well. But I would advise to first think about what kind of things you'd like to explore before you think about how to do that. So as it pertains to unsupervised learning, that is essentially data analysis where you don't have an explicit response variable. So you're not doing something with an outcome of like Y, for example. And so examples of that could be like a clustering algorithm, right? So you're not specifying the relation of your variables in your data set to a specific outcome variable. Rather, you're trying to find similarities and differences between groups or sets of variables. So unsupervised learning really is just data analysis that isn't focused on regressing to a response variable.
Okay, that's helpful.
Yep.
Thanks.
Yeah.
And I have a question about the length of the proposal. or if you have any expectations over the number of the pages or generally the length of the proposal for the project?
Yeah, usually it should be like 20 to 25 page minimum. No, I'm just kidding. Uh, no, I don't care so much about the length. You know, maybe like a page or something like that. It doesn't even need to be that long. But what I would like, or I guess what I would want to see from the proposal is that you started to look at the data a little bit, so you have some understanding of, you know, the size and scope of it. Basically, what you want to get from the proposal from me is feedback that, you know, the data set is big enough for the purposes of the data analysis that we're doing, and also is not too big where it's completely out of scope for what you'd want to be doing as a class project. And then two, that you've thought about the data enough that the analysis will lead to answering some interesting questions, as opposed to like, oh, I have this question about the looking at the data, I have this one particular question which I can answer with like a linear regression. That might be a little bit, you know, too shallow. So, you know, I would encourage you to play around with the data, see if you can get a set of interesting things, and then we can like hone down from there. So really it's an opportunity to get familiar with it and then get a sense of whether or not it makes sense to do for this course.
Okay, thanks.
Mm-hmm.
Hi, Alan. I have a question too. I'm curious, what sort of complexity are you looking for in the analysis? Like what sort of, I don't know, can you give like a brief overview?
I mean, that's kind of hard to answer generically. It has historically has varied quite a bit. I would say don't focus on how complicated it is. I think that as long as you are eliciting interesting questions, that the analysis will sort of follow. And honestly, it can be pretty simple analysis, and that speaks to, in your own research in the future, like you don't do complex analysis for the sake of complex analysis, right? You want to be able to answer the questions that are interesting in the way that makes the most sense. So to me, I care a lot more about coupling tools and techniques to the right sorts of analysis, as opposed to demonstrating that you can, you know, run really complicated types of models, right? So yeah, that's not exactly what I would be looking for in terms of complexity. It's not like a criteria of the project.
That's helpful. Thanks, Alan.
Mm-hmm. Okay. If there's no more questions, let's go ahead and start today. And so today we are, I think everything that we've been doing is sort of starting off with our data analysis, looking at this linear model and sort of expanding it, right? And so we've looked at predictive, so from the linear model, we have talked about more high-level approaches and thinking about prediction versus causality. But then from the structure of the model, we've also talked about going from, you know, one variable to multiple variables, and then figuring out how to select variables in the model. And then we've looked at categorical and dummy variables where your x's are not necessarily continuous, right? And so you may have a binary variable where you have just 2 outcomes, or you may have a categorical variable where you have many outcomes. And that has been focused on the explanatory variables. And so what we're going to begin to do is to talk about, okay, what about if your response variable is not continuous? And so for a lot of you guys who have taken statistics or econometrics already, you may have already heard of this. Or if you've done any choice modeling, you may have heard of this. So this is kind of the next step extension called logistic regression, which is meant to deal with response variables that are not continuous. I think that a lot of the ways that logistic regression is taught is almost as a very sort of separate type of model from a linear regression. But I think it helps to understand like why it is that we do this thing that's called a logistic or logit function. Okay. And so we won't be getting so much into the theoretical aspects of this, but I did want to show kind of the motivation for where this comes from. So a regression model where the response variable is categorical. So we'll start off with simple examples. Where you only have a binary outcome. But we will extend this to multiple outcomes. Similar to the way we went from dummy variables to categorical variables. And so when you have multiple outcomes, this is known as multinomial logit. And I'll note that in the field of machine learning, you may have heard of this. When you guess at binary or categorical outputs, this is also known as classification. Yeah, different fields of data analysis like to throw around their own terms. And so classification is really just one of these forms. So logistic regression, I guess, would be one of the subcategories of classification. But really, it's essentially looking at categorical output regressions. Just a different type of regression at the end of the day. Okay, so more generically, to hopefully put a more relatable example into your heads. Normally what we have here, right, in our inputs and models is a set of continuous outputs, but with a in a logistic regression, what you are trying to address is this issue where you have maybe like a binary outcome. So this might look something like if I had income, education, race, going into a question of maybe like buy a car. And you have yes and no. And again, the main reason why this is different from what we've done before is because the yes and no, when we think about our traditional linear model with x and y, you kind of just have a line. And this line extends outwards to infinity, right? And so so your y can go to positive infinity, and it can also go to negative infinity. But yes and no are essentially these two binary outcomes. And so it doesn't necessarily make a whole lot of sense to do this. Although I will say that sometimes people will still put a type of framework like this in a linear model. And so really quickly, before we dive into the transformations, going to logistic regression, I did want to point out that when you do this sort of approach in a linear model, what you should kind of expect. Okay, so suppose you have your y and your x, and the outcomes are 0 and 1. So you have basically values on your x-axis that can only fall on 0 and 1. So you have something that looks like this. And when people do run a regression on this, you can imagine that if it looks something like this, your line would look maybe something like this. And if there are a whole lot more points in your 0 or 1, for example, it could change the slope of the line a little bit. But what does it mean for an outcome to be sort of only 0 or 1, but then to have your results in your fit be able to take on any sort of set of values like this? The way that people think about this is that they then treat the value coming out of your model, y equals beta x, as so y hat is the probability associated with an outcome. Okay, so that means that if you are closer to if you are closer to these 0 values, right, the probability tends to be lower that you're getting your 1. So it's the probability associated with outcome 1. And that can be a somewhat reasonable estimation of the probability of getting your 1 outcome, as long as you are as long as you're kind of in the middle area. As you get closer and closer to the edges, I think that the probability is probably a little bit less clear, and you're getting to the point where you're extending beyond really where you'd like to estimate. And so, yeah, this is a thing that, for example, economists will do to simplify the interpretation and be able to do sort of a quick and dirty functional form that allows for an approximation of the probability of an outcome. I think that it certainly is reasonable under certain circumstances, but in general, I tend to think that one of the big things that you should always think about is how closely the functional form of your regression matches what you would expect the functional form of the true data to be. In other words, if I have a bunch of points on 0 and a bunch of points at 1, do you think that the relationship between the x and y is actually linear? And if not, why are you doing your linear regression, right? And so that's always something to keep in mind, that if the relationship between your variables isn't being described within the function that you're regressing on as a linear combination of parameters, then you're likely biasing your model in some way.
Alan, can I ask a question?
Yeah.
In this case, if we're using a linear regression model to fit this data, would it be the case that it's a horizontal line in between 0 and 1?
No. And why is that? So we're gonna do okay, so you're talking about this, right?
Yeah.
Okay. So let's see. Which one's bigger, the sum of the red lines or the sum of the blue lines?
Red lines.
Yeah.
Okay.
So your linear regression will want to minimize those lines, right?
Mm-hmm.
So it's unlikely that you're going to get something like that.
Okay, thank you.
Mm-hmm. Okay. So kind of to reiterate what I was sort of just talking about in drawing this blue line through these points. So how do we represent a model to capture relationship to a categorical variable? Okay, so linear to represents probability I can spell, between 0 and 1. So that's probability x, but not bounded. So what that means, right? So 0 to 1. So all the points between 0 and 1 represent the probability that 1 will happen. But it's a little bit troubling because it's not bounded, whereas probability we know has to be between 0 and 1. In the linear model, it's not constrained in that way, so it can extend from negative infinity up to positive infinity. Okay, so a second way we can think about this is that you can take the log of p of x, so multiply inputs together, but unbounded in one direction. Okay. So the way that you might think about this is to do something. So I'm going to do this transformation, which may seem a little bit arbitrary right now, but we'll see why we do this in a moment. So if I take a log of the probability, then let's see. Oops. Log probability to your x. Now your probability will go from so outcome now spans 0 to infinity. So you are opening up the subspace, right? Because from here we are doing better than from going from 0 to 1, because now we're going from 0 to infinity. But really what we want to do is to be able to go from an outcome of negative infinity to infinity. And so the form of this is if I take a log of the odds ratio, and so this is known as a Logit function. And again, I'm not going to go heavily into, or too heavily into the theory here, but the main idea is that, okay, so if I think about what odds are, so odds is equal to the probability of an outcome over 1 minus the probability of that outcome. So this is the probability of success, and this is the probability of failure. So if you have like a 10 to 1 odds, that means that the probability of your success is 10 times larger than the probability of your failure. And if I were to graph this out, so if y is equal to p over 1 minus p, in other words, this is your odds, and this is your probability, the graph will look something like this, where you go 0 all the way up to 1, and this will extend as p goes from 0 to 1, y goes from 0 to infinity. And if I take the log of the odds, log odds goes from negative infinity to infinity. Okay, and so the main thing I'm trying to show here is that you can manipulate the functional form of your model so that when you do your regression, we are able to still go essentially, we can transform the model so that our outcome variable still goes from negative infinity out to positive infinity. And that makes it a lot easier for the regression to essentially, or to come up with an analytical solution for a regression. And so this is, the logistic regression really is just a way of transforming your model to fit a sort of function that allows you to regress across a sort of full range of values. Okay, so there's a question, is there any difference between logistic and logit? If the probability is not bounded in the logistic regression, how do we interpret the result which has greater than 0 probability? Yeah, so I'm going to show, okay, so the logistic and logit function are just abbreviations for each other. If the probability isn't bounded, so the probabilities are always bounded. Probabilities can always only go between 0 and 1, but we change the probability into odds so that we can go from 0 to infinity, and then we change the probability, and then we change the odds to log odds so that we can go from negative infinity to infinity. And you can figure out the value. So when you do the regression, you end up with this crazy log odds thing, which I tend to think is a really weird thing to interpret. And so you can always actually transform back from the log odds into probability, which is what I sort of always suggest that you do. And it makes the interpretation of the results much cleaner and much easier, even if it's not sort of linear. And so I'm going to show an example of how to do that, sort of theoretically, and then we'll apply that in R. So hopefully, I think that will answer your question. That definitely, I think for sure, one of the things that folks get hung up on, and I still do too, after being exposed to this for a long time, is being able to interpret the results of a logistic regression, sort of the raw results of saying, okay, changes in this change in X leads to this change in the log odds ratio of the outcome, which is a little bit nonsensical. Okay, so let's do, okay, wait, I see another question coming up. So when analyzing the relationship between Y and X, why do we bring in probability? Okay, so if you only have, if your outcome for your Y can only be a 0 or 1, I guess it's a little bit less interesting. Well, so there's two things I'm going to talk about. The first one is it's a little bit less interesting to just say the model predicts 0 or 1. And actually, you can do that, but you actually get more information if you talk about the probability that the outcome is 0 or 1. And then if you really wanted to, you could take those probabilities and then you could filter to assign to a prediction to see whether or not or how close you are to your outcome. So like if you're flipping heads or tails outcomes, then you can imagine that that there are two models that will both give you the right outcome for getting 1 or 0 or getting a heads or tails. But in one of the models, it may assign like a probability of 99% that you get heads, and in another model, it may give only a 51% that you get heads. And that tells you something about something additional to just the outcome of getting the heads, but also how likely you are. So I think that there is value in doing that. And then the other reason that we bring in probability is that in all of these regression models where you have these continuous outcomes, how else are you supposed to get like a 0 or 1, right? If we're doing it in a linear regression, we call it a probability because your fit is going to land somewhere between 0 and 1. And so you have to have some way of interpreting that. So we just refer to that as probability. And then it's a sort of natural extension from there to think about your outcome as a probability of getting a particular 0 or 1 outcome or categorical outcome. So hopefully that makes a little bit more sense. Okay. So if I go from my log of p of x, or 1 minus p, oops. So this is my y. Oh yeah, I should also mention, because this has been confusing in the past, and I always forget to make a note of this. P of x doesn't refer to the probability of x. P of x is the probability of y given x. So really, you probably want like a little subset like y here. So don't get confused. I'm not talking about the probability of x here. I'm talking about the probability of an outcome given a value of x. Okay. So in this logistic model, it looks something like this. Okay, so given an x, there is some kind of linear beta combination that gives us the log odds ratio for y. But like I said, I think that the interpretation of the log odds ratio is fairly weird. And so really what I care about is what is the probability of my outcome, right? And so what's the probability I get heads or tails? What's the probability of a particular choice? And so what we're going to do is we're going to transform our linear model of the log odds into some, weird non-linear model of the probability. So if I'm interested in Py of x, I can solve for it, and what your solution will end up looking like is, okay, maybe I'll do it like this. E of beta 0 plus beta 1 of x divided by 1 plus the exponential of beta 0, beta 1 x. And so some of you guys have probably seen this form before, but this is how we sort of arrive at this. And so this is known as the inverse logit. Okay, and so with this equation, you can solve for your betas, and then you'll be able to calculate the probability of a particular outcome. Okay. Are there any questions here? I'm gonna go from here to show how we would do this in R and how we would go about kind of interpreting this. But I do want to pause here in case there's any confusion. I will say that I do recall when I was learning this in grad school that this was super confusing. And being familiar with it now can kind of make me distance myself from that confusion. But let's see. Questions that are coming up. So if in my data set of binary logit model, 50 people say yes, which means 1 to the dependent variable, will the sum of my predicted probability from the logistic regression be near 50? Let's see. Well, the sum of my predicted probability. Yeah, that's an interesting way to put it. I have never thought about it like that before. I don't. I'm not sure. Probably. We could actually look at this because we're going to do an example, and we would be able to calculate that. So that might be kind of interesting to see. I think in theory, it kind of makes sense that it would be, as I kind of think about it, because you have points that will be close to 1 that represent the 1 and points that aren't, but those are always going to be smaller than 1s. So the 1s will be lower, but then for the 0s, it's going to be higher than 0. So yeah, possibly I could see that happening. I've never quite thought of it that way, but we can check with the real data set. is, okay, so I see a question, is X a categorical variable in the Logit model? So it can be. In the example that I'm giving, I'm kind of assuming that it's continuous, but the treatment of your X in the categorical, in a logistic regression model certainly can be categorical as well. You just have to, again, be careful about how you interpret it. But what we've learned so far in terms of continuous and discrete X variables is definitely applicable in these logistic models. Okay, so Greg is asking, so do we first do a linear fit of the data, then plug that into the inverse logit to get P of X, then plug P of X into the log function? Yeah, okay, so essentially what you're asking is how do you solve for the betas in reality? So the way that it's traditionally done is actually it's actually in this form, in the inverse logit, to calculate the probabilities. And the technique that's done, so in ordinary least squares, it is an optimization that reduces the size of the squared error. In a logistic regression, it's slightly different. It does what's called maximum likelihood estimation using a likelihood function. And so what it's doing is a different sort of optimization that is maximizing essentially the plausibility of each of your model parameter values. This is where I depart a little bit from having to teach the theoretical aspect of it. What I will say is that unlike in ordinary least squares where you have this what is it, xtx minus 1 y x, something like that. I always forget. Ytx maybe equals your vector of betas. This is like a closed form analytical solution as opposed to the maximum likelihood estimation, which is a numeric optimization and solver. So it solves it. It solves it numerically rather than analytically, which can have important implications. So if you're definitely more vested in doing choice models and that sort of thing, it's worthwhile getting into some of these nitty-gritty details. Giovanni teaches a class on discrete choice modeling that will give you a lot more theory about solving these what goes into solving these. For this class, we're sort of like, hey, that's kind of a black box. We're just going to show you how to do it in the code. And then I think really what I want to nail on is understanding when to use it, why to use it, and the interpretation of it. Okay, more questions popping up. How does logistic regression relate to the arena of discrete choice modeling, which often uses logit models? Logistic, I remember being told that logistic regression is not the same as a logit model. Okay, maybe what I'm saying is a bit of a misnomer. So a logistic regression uses a logit function, which is this thing over here. And so, they're not like strictly the same per se, because the logit function is referring to a functional form, but the logistic regression is referring to basically solving this whole problem. So the logistic regression employs a logit function in its functional form. So I guess the analogy would be OLS is to linear as logistic regression is to logit, if that makes sense. Yeah, so there's no, okay, no more questions are really popping up, but again, from sort of my own experience, I do recall this as being sort of a fairly confusing topic. So, do take the time to review this material and make sure you understand it. And I've spent some time making some more detailed notes, which probably do a better explanation than what I'm giving right now. So review those to make sure you understand what's going on. And let's go ahead and move to looking at this in R. And I do think that that this can help with sort of the understanding of what's going on here by looking at an application in a real world example. So give me one moment to pull this up. Hang on. Ruh-roh. My notes are blank for some reason, but that's okay. We'll just pull up the notes from last year. Actually, while I fumble around with this, why don't we actually take our mid-lecture break for now? So we'll do a 5-minute break. Feel free to ask more questions in the meantime, but I'm gonna take some time to pull up my previous year's notes.
Hey, Alan.
Yep.
For the project, would something like a simulation model that does like optimization, like of some outcome, be a type of project we could do for that, or is that kind of outside the scope of this class?
Yeah, I guess I would say that's a little bit outside of the scope. I think that what you want to be doing is essentially being able to analyze data as opposed to like simulating your own sort of outcomes. I think that would be more apt for like some more like a modeling based class.
Okay.
Yeah. One of the primary criteria is having a data set to look at, and so you'll want to be able to essentially analyze some kind of data set. Okay. We are going to look at running a model using this election data. And so let's quickly take a look at what's in here. It's a pretty simple data set. It is, let's just click here. So there are 72,000 observations here. And this is looking at different districts historically across the country in the United States, and looking at the percentage of registered Democrats among all registered voters, and then in any particular election, whether or not the Democratic candidate won. Okay, and so here we can see if we want to get some sort of sense of given a percentage of registered Democratic voters, how is that related to the outcome of a Democratic official being elected, which is a binary outcome, right? They either win or they lose. And so we will be doing a logistic regression. So I'm going to create an election model. And so the function that we use here is called GLM. So this is used to fit, this is known as a generalized linear model. And so the reason why we call it a linear model is because it is technically still linear in parameters to look at the log odds, right? So the functional form is not linear among my x to my y directly, but it is linear in the transformation of the y. So this is the R function that we use. And so we want to regress Democrats winning on the percent of the voters who are Democratic. So we'll be using election.data. And then you have to list a family for a binomial outcome. And that's, so essentially what we're saying is you are going from something like y equals beta x plus alpha plus epsilon, and you want to change this to some sort of f of y is equal to beta x plus this. And so it needs to know what this function is. And so when you specify it as binomial, it's going to change it into your logit function, essentially. So that's what's going on here. Okay, so let's go ahead and run this. So the first thing that you'll note is that when I ran this, it took kind of a hot second for this model to solve. And again, this has to do with the fact that solving this model is really different from the way that a linear model is solved. And again, it's not something that we're going to get hugely into, but there is a sort of fundamental difference. And some of the models that run logistic regressions, you'll get these sorts of outputs, and we'll probably show an example of that, where it is doing this iterative process to solve for your betas. Yeah. So this is the output of the regression. Okay. And let's see. The model that this particular set of outputs is describing is this whole thing where we have the log odds is equal to beta 0 plus beta 1 of x. And so when you look at your coefficients here, the intercept here is describing beta 0, and this percent Democrat is describing this beta. And I'm actually not even going to attempt to do the interpretation. I always get it wrong. They teach you this in classes where you're learning about logistic regression, but like I said, it's it's really counterintuitive to do the interpretation, and actually the interpretation kind of changes because it depends on the level of your x. And so I don't really want to put it this way, but the betas are a little bit nonsensical in that it's difficult to interpret just straight up the log odds ratio. You can make some qualitative judgments about what these betas are telling you. So like the fact that percent dem is positive means that as you increase the percentage of Democrats, it's more likely that the outcome will be a Democrat winning. But like that's also kind of like a silly thing, right? Because it's kind of obvious, right? And obviously, you could be looking at data and models where maybe it's not so obvious. So there is still some value in just the like quantitative aspect of the positive and negative values. And then you could also look at the values in relation to each other. So if you're doing multiple x variables, if the coefficients are a lot larger for one, then you could argue that like a marginal change in one of these things leads to a greater change in the log odds that your outcome of interest is being affected by. So looking here, even if you're not able to necessarily interpret what the betas mean quantitatively, you can be able to make some judgment calls about the direction of the effect and how big the effect is relative to other variables. But as I mentioned before, I personally think that you should always do a transformation of this back into the probability space, okay? And that makes these results way easier to digest. And the only drawback is that it's not linear. So what we're gonna do is to do exactly that. So I've created a new data set, election.data.new. And that looks like this. So it's basically looking at different percentage Democrats. So this is, if you guys can envision kind of what we were doing before, we want to look at predicting using the model that we just generated as I go from 0% Democrat up to 100% Democrat. What's the probability that that a Democrat wins given our model? So we're predicting, and then we're going to use new data where we've we're going to use new data where we've specified the percentage Democrats ourselves. So this option at the end, type equals response, that's the thing that will give the percentage outcome. You can actually get all the different sorts of Y outcomes. You could get it as the odds, you could get it as the log odds, you could do the transformation yourself. But when you have type equals response, it'll give you the probabilities. So let's go ahead. Okay, so actually, I can look at what that looks like. So probability that the Democrat wins looks something like this, and I'm going to go ahead and graph this so we can see what this looks like. Okay, so using the predicted data set, I'm going to look at the percent Democrats versus whether or not they won, or the probability of whether or not they won. And so if I go ahead and run this, we should see this plot here. So this is kind of the quintessential plot that you see out of logistic regressions. This will provide the probability of my y equals 1, and so it will look something like this. So as I have a higher proportion of registered Democrats, the probability that the Democratic candidate wins is like so. So this gets back to a couple of the questions that were asked earlier. So why is it that we don't just do zeros and ones? Well, here we could go back to apply. We could apply this prediction to see whether or not it's 0 or 1, and that's actually a set of diagnostic tools that you could do for this. You could look at type 1 and type 2 errors, so false positives and false negatives for specific outcomes. And there's actually a thing that you can do in cross-validation where you modify your betas to minimize a certain type of error, right? And that can be really important for, say, if you're in like the medical field. If you care more about false negatives than you care about your overall error, you could actually tune your betas, right, to reduce the false negative rate or the false positive rate. And we may talk about that in this course if folks are interested and we have time. The other thing that I want to talk about here is that this type of graph is actually so we'll extend this type of graph into multinomial logit, which I'll talk about in just a second. But the thing to know about this is that this line here is describing probability that Democrats win, okay? There's always actually a corresponding line, or in a multinomial logit, a corresponding set of lines that describe your other outcome. And what does that line look like? It looks something like this, okay? And this is the probability that Democrats lose. And the sum of these points at any given x value, right? So here, this sum probability equals 1, right, at any given point. So if I were to say here at like 60% of registered Democrats, there is some probability here in red, and there is some probability here in black. And the sum of those probabilities always has to add up to 1 at any point along my x-axis. So just know that, right, when you're doing these probability graphs, that you actually have these corresponding probabilities. And that'll be, I think, really extra helpful when we think about this in terms of interpreting a multinomial logistic regression result. Okay, I actually wanted to, for curiosity's sake, look at the other question that was asked about whether or not the sum of the probability values will be close to the sum of the actual outcomes. So there's an easy way to do that. Let's see, I'm just going to call it hold, is predict election model. And oh wait, but I want the type equals response. Oops. So let me take a look at this to make sure it's what I think it is. Oh, I can't actually look at it. Hang on. Yeah, okay, so these are probabilities. Okay, so what I want to compare is the sum of the predictions, and I want to compare that to the sum of, in my election data, dem1. So there was an earlier question asked if the probability, if you add up all the probabilities of your model, whether or not it's going to look like, the sum of the probabilities is going to look like the actual outcomes. So this is 41,366, and this is 41,430. So pretty darn close, yeah. Kind of interesting. I've never thought of it quite that way, but actually, this I guess yeah, in machine learning, yeah, now that I'm kind of connecting the dots here, this is actually getting back to the error in the machine learning. So this, when we talk about types of error, it's not going to be quite the same, but one way that I can force my model to give a outcome. So if I wanted to go from probability space into a discrete outcome, the way that most people would do it is that you basically make a cutoff value. So here I would say if the probability, if p is greater than 0.5, then you assign the particular outcome as a democratic win. And if p is less than 0.5, then you say the Democrat lost. And then you can use that to calculate your error term. And what I was saying earlier about the type 1 and type 2 error is that you could care more about this value and sort of ignore the other one if you want to look at, okay, would this be type 1 or type 2 error? So if our outcome of interest is, the Democrat winning, and you get that wrong, in other words, you predict that they didn't win, that would be, sorry, if the probability was greater than 5, but then they didn't win, that would be a false positive. So this is essentially how you would get at the false positive and false negative values, is by looking at converting your probability into the actual ones and zeros and comparing to the actual ones and zeros, and then calculating the respective errors that way. Okay. So let's see, we still have a little bit of time, so we can jump into okay. I don't think I quite have enough time to talk about the full set of stuff for multinomial logistic regression. So we'll talk about that next class. But actually, in the meantime, since we do have a little bit of time left, we will talk about, we will get into a little bit of theory here. Okay, so let me go back to the whiteboard. Actually, before we go back to the whiteboard, does anyone have any questions about this? No questions. Okay. The way in which, so I had talked about this a little bit earlier today. When we estimate an ordinary least squares, that is the minimization of the error term between your fit and your actual data points. And that is not how we estimate the betas in a logistic regression. So what we do in a logistic regression is something called the log likelihood function. So this is not, again, this is getting a little bit into the theory here. It's not what I expect you to take out of the class. I think it's a lot more important just what we just covered, at least for the purposes of what we're doing in this class, to get a really good firm sense of when you apply this model and the interpretation of it. But that whole thing, when you press enter for solving the GLM function, I do want to give a little peek behind the hood about what's going on. So the log likelihood function is what's actually being solved for, or what's being optimized on. And that is a function that is describing the plausibility of a model parameter value given specific observed data. So the log likelihood function for beta 0 and beta 1 would look something like this. I equals 1 to n. So for each so I is referring to each observation. So yi times the log of probability of xi plus 1 minus yi log 1 minus p of xi. So if you are curious as to where this sort of comes from, this is derived somewhat from the Logit function. So if you take a log, if you take a log of the Logit function, there's a transformation that allows you to go into the log likelihood function, which again, I'm not going to sort of derive here, but you can hopefully see some of the similarity in terms that are being shown here, right? This sort of 1 plus e to the beta 0 plus beta xi, that's the denominator of your inverse Logit function. And then you have something like this. Beta 1. And what's happening behind the scenes is this equation is the thing that is getting solved for. So when you hit enter on the GLM function, R is going to do this. It's going to set partial derivative equal to 0 for DL with respect to D log likelihood for each beta. And then it's going to approximate this numerically. So this is, again, to reiterate, the stuff that's happening behind the scenes. I'm kind of providing this as reference material, but you won't need to like memorize this or really know this for the purposes of what we're doing in this class for like the homework or the project or anything. It'll be essentially the implementation of this via solving it in the code, which is done for you sort of automatically. It's kind of the balance that we have to play in this class about covering the theoretical aspect, and being able to expose you to a lot more of the materials and tools that you use in data analysis, which is why I sort of skim over this. And I think it is kind of important. So as you get exposed to these sorts of tools, if you find yourself really doing lots of this particular type of data analysis with discrete outcomes, right? So thinking about like choice modeling, for example, then I would highly encourage you to get a little bit more fundamental understanding of this sort of material, which you can find in other classes offered at Davis. I know that both Giovanni and David Bunch teach classes about more advanced topics in discrete choice modeling. So you'll learn a lot of this stuff and more. And there's more than likely a couple of classes in statistics that cover this sort of stuff as well, or the theory behind this sort of stuff as well. Okay. I think we're actually going to end early today, because if I get into multinomial logistic regression, I don't want to end up kind of halfway through it. So we'll hold off on that until next lecture. And in the meantime, since there is a little bit of time left, I can make myself available for not only questions related to this, but if folks want to talk about, projects or the homework, if you've started looking at it since I posted it yesterday, or maybe I posted it on Tuesday. Yeah, I'm open to that. Otherwise, we'll end early for today.
I have a specific question about a project idea, but I can
Sure.
wait. There's some other general questions that people have first.
Yeah, we can hang around for a little bit. Or you can go ahead, because it seems like doesn't seem like there are questions. Actually, let me end the recording.